Can everyone hear me clearly from the back? Louder? Okay.
Okay, our next speaker, Jingwen Zhang from UC Santa Barbara, Finding the Great Sculptors.
Hi everyone, my name is Jingwen Zhang. I'm a postdoc at UC Santa Barbara. I'm happy to be here today to share with you about the project to search for planets in the Bradic system. The Bradics are relevant from planet formation process, and any planet can dynamically interact with them. And an example is our own solar system. We have two Bradic, the astral belt that is beside Mars and Jupiter, and the Kuiper belt outside Neptune. The studies of solar system has revealed the Bradics can dynamically defined by the inference from the planets such as Jupiter and Neptune. In actual solar system, we also have a few detection of both the Bradics and the planets in the same systems. A well-known example is the Beta Peak system. That is a very good example show how the interaction, and we can use observation of the Bradic to predict the location of the planets. And the Bradics appear to be in a variety of morphology, and many mechanisms have been proposed to explain the interaction between disk and the planets. Today, I will focus on one of the most common ideas, the sculpting effect. Observation has shown that the Bradics tend to have sharp edges instead of diffuse boundary. And to explain why their edges are sharp, a plausible mechanism is there is a planet just right inside to the disk, and the planet will clean out the material from the nearby region to cause the sharp edges. And based on this theory, people have came up with a hypothesis as if we observe the Bradics inner edges, we can use this to predict where the planet and how massive the planet should be. And for example, I'm showing a model that's just assume one single planet sculpting the disk. And the vertical orange line is the location for the inner edge of the disk in the system. And the planet need to follow the green line here to be able to explain to responsible for the sculpting. Another constraint comes from the timing. The planet need to move fast. They need to be able to clear out the material shorter than the age of the system. So any solution that's above the yellow dashed line is possible. That gives us a minimum mass requirement for the planets that could be used to explain the observed inner age of the disk. Use this methodology. Pierce 2022 have proposed a population of planets that based on the observation of the Bradics. And here I'm showing those population in orange circle. And I also put the non-planet from NASA Exoplanet Archive here. You can notice this population is in a perimeter space that has not been touched by current technique a lot. Their masses tend to below the detection limit for ground-based direct imaging observation so far, but that has changed since the launch of GWST. GWST, here I'm present the sensitivity for the near-cam observation, and you will find GWST's sensitivity has covered almost half of the perimeter space in the population. And the recent discovery of a planet in the TWA7 system have demonstrated the power of GWST, and this system is also a system with the Bradics, and the planet has estimated mass just comparable to Saturn. So our program is trying to looking for any possible target for GWST from this predicted population. And we calculate their detection probability based on their ages, their separation, and the masses, and select those targets with probability for detection above 50%. And here we end up finding a total of 21 targets we think GWST might have the chance. And among them, almost half of the target has been included by previously approved program. So our program are targeting the certain system that has not been observed before. And today I will focus on those observations from our own program, but in the future we plan to include all the data from the archival, so that will make our sample larger and more complete. The science question for this program is to answer the occurrence rate of the planet that could sculpt the debris disks. And let me show a few examples of observation from our program. And all targets were observed in two filters, one filter at about 2 micron and another filter about 4.5 micron. This can give us the information about color if any interesting source pop up. And also we also detect some debris disks with very high quality for the data you can see on some system here. And I want to introduce one of the systems we trying to study first, because first we detect a face-on debris disks in the system. Also we find a point source, point-like source in the 2 micron, but that is not seen in the 2 micron. This is originally we said it's an exciting sign because it is consistent with expectation for planets. Planets are should be much fainter in 2 micron compared to 4.5 micron. And until recently, we realized this target is as part of the ARC survey to image the debris disks use ARMA data. So we reached out to the team and got information that they also see a very bright source in a very similar location in the ALMA observation, as I shown in the right. And they kindly provide us the astrometry from the ALMA observation, which we can use to estimate whether this source is bounded to the host star or not. And in this case, unfortunately, our calculation is consistent with that this source is actually a background object. It's most likely a background galaxy. We keep looking for other additional sources in the residual, especially the one after subtracted the disk model, but we do not detect any additional promising sources. From the residual, we can start to build up the detection probability map, that is, in which parameter space we will have the chance to see the planets. And here I'm also overlap the inner edge of the disk as the dashed line here. In the beginning of the talk, I have shown you the model that is we can use the measurement of the inner edge to predict where the planet should be. And here it is the model result for this system. So the planet that could answer or could cause the observed inner edge of the disk should follow the blue track here until the gray circle, which is the minimum mass that's from the calculation. And we can also estimate the detection probability inside the parameter space that consistent with the model prediction. So if there is a planet that is inside the black box I just marked here, we will have 84% chance to see it. It's a pretty high chance, but instead we do not see any planet or planet candidate yet from this data set. And I have also done this analysis to other system inside the sample and have an estimate about what the chance we will see it if there is a planet sculpting the disks predicted from the model. We identified a few sources, but most of them have been ruled out as background object. And although there are some undecided sources, but they are not inside the black box I just marked here, that could be used to explain the inner edge of the debris disks. So although we have pretty high chance for many of the systems to see the sculpting planet, we do not see any of them so far. And the non-detection here sounds not that good news, but actually it can still provide us the information to answer the original science question we want to answer in the beginning, that is what occurrence rate of the disk sculpting planets. And here I'm using the Bayesian model. The parameter I'm trying to figure out is the frequency of the planet. That's the average number of planets per star in the sample. And the observation we have is the number of detection and also the detection probability I just showed you. And because we don't have any detection yet, we only have an upper limit in the calculation. At 2 sigma, the frequency is below 0.48, and 1 sigma is below 0.17. And I will highlight that this is only preliminary result. We only consider about the system that's from our program, but in the future, if we add the additional target from the archival data, the sample size will be doubled and uncertainty will become smaller. Although the result is still preliminary, this, we begin to emerging to see the answer for the occurrence rate of the disk sculpting planet is quite low. And how we can explain that? The first possibility is maybe the model of a single planet sculpting the debris disk is too simple, and it's not the case. And if we assuming multiple planets sculpting the disk together, the required minimum mass will become much lower. That below the detection limit for the GWC observation. A second possibility is those planets might have migrated inward. They might do not see in the the previous location, but going to a much closing orbit. Then there will be not possible for GWST to observe. But a very exciting opportunity is that by the end of this year, we will have the time series astrometry from Gaia 4, which could give us the opportunity to detect those planets at a few AU around young star and around the debris disk system, and can give us the chance to answer whether there's an enhanced population of giant planets in those systems. And the third possibility is maybe they are not related, and we need to find other mechanisms to explain why debris disk has such sharp edges. And I will stop here. I found it's a very good takeaway slides for people to get the key point from my talk, and I'm happy to answer any questions.
Hi, nice talk indeed. Yeah. You were mentioning Gaia DR4, and I'd like to mention that we did the exercise with Gaia DR3 data on all debris disks. The paper is now being in revision. It would be interesting to see if we can couple the results, because we have it really well extends the limits that you are showing, as you were mentioning. So we already have some data on that.
Yeah, I think you say currently the GADR3 data is available, that we can have some analysis.
We do have this analysis ready, if you are interested.
Yeah, that would be very interesting.
Jingwen here. Oh, okay. Hi. Great talk. My question was, how do you think Roman can improve these constraints that you've drawn on the presence of planets at the inner edge, or better understanding what's happening at those edges?
Yeah. So Roman has very different field of view compared to GWST. But yeah, I think this is a good plot. Like show Roman will see the separation at much close-in area that could be possible for detection. Yeah, Jason.
I was wondering, for your second scenario of the planets migrating inwards, how would you still create a sharp disk inner edge if the planet was no longer there to carve out that sharp inner edge of the disk?
Yeah, that's a good question. If this is the case, that means the sculpting should happen very quickly. They sculpting the disks and leave a very sharp edge and then move inward.
It would also depend on the time scale for the disk to repuff, because the disk itself, the disk particle, the dust in the disk will interact and puff itself up as well.
Yeah. That's also the limitation for this explanation.